Hello. Hello. Okay. Hello, everyone. My name is Ugur. I'm a PhD student at Boston University, and this is Matt Benjamin.
Hi there. I'm the downstream Ceph engineering manager for Red Hat Object Storage, which means I'm a Ceph developer and S3 Object Storage developer working on Ceph.
It's better? Okay. So today we're going to talk about the D3N projects and its future directions. So we have been working on this project for the past 2 years. Today I'm going to talk about our new algorithm that we developed for cache size partitioning. So let me briefly review the problem. So D3N designed for improving the performance of big data applications in data centers with imbalanced network. And a typical private data center with a data lake has network congestion and high latency fetching data from the data lake. And congestion and latency happens because of the organic growth of the data centers and the oversubscribed networks. These are results in network imbalances and impact the performance of applications. So we propose a solution, D3N, which is actually a multi-layer cache architecture for the data center, where we place strategically shared object caches across the data center. And the main idea of the D3N is caching the data on the access side of the bottlenecks. So I'm going to go over the architecture. So as you see, we have a backend storage, we have a hierarchical network topology, and we have racks, which contains a bunch of computation compute nodes. And we place rack local cache servers on each rack. These servers are equipped with high performance SSDs. And then we are running cache servers on top of these cache services on top of these cache servers. And then D3N allows you to group cache services into pools and create layers. So you can group them and create layer 2. You can group them and create like higher layers like layer 3. So we implement this architecture into the Ceph Rados gateway, which is the object storage gateway for Ceph storage, and we are upstreaming the code. So any application that supports S3 or Swift compatible object interface can able to use it. So in the current implementation, we are only supporting the first two layers, layer 1 and layer 2. And these two caches are collocating on the same Rados gateway. And we are caching the data across the SSDs. So last year, I present some of the results. So we evaluate the cache, and we have like a great performance improvements. So as a summary, we run realistic workloads, and we see the performance of the runtime improved by 3 times. And we show that multi-layer provides higher throughput than single-layer distributed caches. And we show that D3N actually saturates the disk and network speeds. And up to this point, we were like statically allocate the cache size between layer 1 and layer 2. And I just want to remind you that these two layers are collocated on the same cache. And then during the summer, we were studying another problem of how should we partition the cache size across layer 1 and layer 2. So we come up with the algorithm which partition the cache space between these two layers based on the observed access pattern and network congestion. So you may have very high cluster locality in your cluster, or you may have a very high congestion to accessing the storage backend. Then in this case, you would like to keep the size of layer 2 bigger. It could be the opposite. You may have a lot of like rack locality, or you can have a lot of congestion within the cluster among your racks. Then in such a case, you would like to increase the size of layer 1. So we come up with an algorithm, and the algorithm calculates the reuse distance histogram using a shadow LRUQ, and then monitor the mislatency and calculate the mean mislatency for each layer. D3N, using these two metrics, try to estimate a potential miss numbers for each layer, and then trying to find a partition point which minimizes the mislatency. D3N run this algorithm periodically and then adjust the cache sizes. I can discuss offline the details of the algorithm. And then we evaluate the algorithm using a trace-based simulation. We run Hadoop, Facebook's Hadoop traces, and the simulation simulates a data center with 10 racks and a fat tree topology. And we compare our findings with the static allocation. So we first look at the reaction of the D3N when the access pattern change. And we show that D3N adapts very quickly when the access pattern change. And its performance faster than static allocation. And only layer 2, this means a state-of-art distributed cache such as Alaxio. So D3N improved the runtime of, dynamic caching algorithm improved the runtime of jobs comparing to static algorithm by 15% and comparing to distributed cache like Alaxio 35%. And then we look at when the network load change, when there's a congestion somewhere, does D3N adapt it? And we show that it adapts again very quickly, and it's also improved the runtime comparing to static allocation by 20%. And finally, we evaluate the performance of dynamic algorithm under different locality levels, from everything is rack local to cluster local. And again, we see high performance improvements. Now Matt is going to talk about the future direction of the projects and the collaboration.
Okay, well, I'm not going to talk about this slide terribly much, I'm probably going to point out that, that my role in this project is arriving a bit late, but I'm part of an extended team that's been working with these researchers for a couple of years, and we're interested in adapting the core Ceph object storage technology to better serve scaled analytics workloads, and we're particularly interested in strategies like caching, with intelligent prefetching, which we think is an important way to accomplish that, but also feeding back those kind of strategies into the applications that consume the object storage. So, in addition to helping out in guiding aspects of implementation, we've been working with customers of Reddit object storage in various environments, particularly big data and data lake sort of applications, collecting additional traces, and hope to use those to feed back into the work being performed.
And for the future direction of this project, now we are looking at eviction, admission, and prefetching policies for multi-layer cache. We are trying to characterize the access patterns to the object stores by looking at different workloads. We are interested in like fair sharing and cache prioritization, and we are also interested in caching intermediate data sets using write-back cache. And we have a web page for the projects, and the code is on GitHub if you are interested in it. Thank you very much.